Okay, so we're going to take a look at constructing two blocks in a 2 to the 3 2 series. And those two blocks must be of size 4, right? So this is going back to that example from the previous set of notes. Let me flip up in the book. This is on page 388 in the text. So notice here, this is the contrasts, all possible contrasts for a 2 to the 3 design. This is the one where the specification of the grand mean is positive in all cases. If we go to example 15.1, this is what I wanted us to step through together and make sure we understood. Then I'll get back to the notes. Okay, so we want to confound a 2 to the 3 into two blocks of size 4. That, remember, it means we're going to throw some of those effects under the bus when we do this. We need to use the ABC interaction as our defining contrast. That way, that's the one we can reduce to in order to be more efficient in our design. So if ABC is our highest order interaction and makes our defining contrast, then we have our pattern of plus minuses. Looks like table 15.1, which of course was the one we just looked at, where it defined all the contrasts for the 2 to the 3 design. So using that table, make sure you can confirm that this is the negative block. This is the positive. Well, I guess it doesn't have to be negative and positive. We could reverse that. Okay, so we can easily see that here. You can imagine how as your design gets very large, this gets a little bit more cumbersome, I guess you'd say. Let's see. We're going to use our EvenOdd rule, okay? So let's read through this section. So first we use the EvenOdd rule. Almost every experimental design textbook will use this rule at some point, and it's fairly simple. What you want to do is look at the letter designations here for our two blocks. Notice these are our two blocks of size 4 each. And divide the factor level combinations into two groups, depending on whether the letters of a factor level combination contain an even or odd number of letters from the defining contrast. So what's our defining contrast? It's ABC, okay? So we're going to use that as our defining contrast as we run through this. Let's go through and use then Gary talks about the 0-1 rule. It's kind of the same idea. We work with the numerical 0-1 designations for those factor level combinations. And then we compute each factor as a sum of the 0-1 level indicators. Let's just see this. I think this is really hard to see in practice or see in general until we see it in practice. Okay, so for the defining contrast ABC, we can compute L, which is going to be what determines what goes in each block. So you can see here I've got the block set up where we had just used the effect coding, but here you can see if we just have A, that leaves modulus 1, so it goes in that block. Same thing with B, same thing with C, or ABC, because then we'd have 3 mod 2, which is 1 mod 2 and the others. For all of the others, we get a modular of 0, okay? If none of them are present, it's 0. If 2 of them are present, whether it be AB, AC, or BC, then we get 0. And so that's what defines that blocking for our experiment. So we've actually got kind of like 3 ways we can go about it. Just take some time, read through this, make sure you understand. We'll practice it too. All right, so 2 blocks of 8 and 2 to the 4. This is what's in the notes, and let's just take a look at it here. If we choose blocks using our EvenOdd rule, first we find the letters from each factor combination that appear in the defining contrast. What's our defining contrast? It's, in this case, he's changing things around. It's going to be BCD. Okay? So for the even-odd rule, again, we're going to find the letters that appear in that contrast. So table 15.2 here gives us those levels. Let's begin with a match. I think it makes sense. In the effect B, our match is B. That's pretty obvious, right? So it gets coded as odd. But let's compare that to A. Remember, our defining contrast is BCD. A does not contain a match, so it gets coded as even. Same thing with the grand mean. It does not contain a match. So far we see A and the grand mean in block 1 and B so far in block 2. If we go to our first interaction, AB, the only match is B. And it's an odd number for the match, so it gets coded as odd. And so notice AB ends up in block 2. C, odd, just one match, odd number. AC, also odd. So notice we're down to that fourth effect in block 2. Then we get to BC. So BC has two matches, B and C. Well, that's an even number, so it gets placed in the first block. Notice the pattern. Let's take a look at something a little more interesting. Maybe our first three-way interaction. A, B, D has an even number of matches, so it gets placed in our block 1. But B, C, D all match, so it's odd, as with A, B, C, D, all B, C, D match, so it gets placed in odd. So notice how that splits it, evenly divides our effects. So make sure, this seems like kind of a weird, trivial, I guess in a sense, exercise, but maybe take a little time and use the 0-1 rule. I kind of like that one better, only because I think it's simpler to think about modular effects than anything else, and it goes along with the effect notation or the coding notation I prefer here. So read through this, make sure you understand that. So now let me go back. I think I've given you enough background now that we can get along with the notes. Okay, so this, here we have ABCD confounded with two blocks. So let's use, we can just kind of think of this, if we use our modular and we code this using the modular or 0-1 coding rather than even odd. We have ABCD showing up and we have 4 modular 2. So it's 0, okay? Notice if we use even odd, our number of matches is 4 with that effect ABCD. So we have an even, all right? CD, we have even. BD, even, or modular. The modular result would be 2 mod 2, so 0. All of the 2-level interactions are going to be even, along with the main effect, because that grand mean, or I should have said grand mean rather than main effect, is going to be 0, 0, 0, 0. Okay, all the other effects, notice they're odd when you use the even odd notation, or they are modular 1 if you use that notation. But if you want to do ABC, you get the following. I want you to run through this. Sometimes making sense on your own is more effective than listening to my somewhat convoluted explanation. So run through this on your own. Make sure you know why, it doesn't have to match like the positives, the negatives in terms of your exact group 1 or 2. You may like reverse 1 or 2. That doesn't matter. That's kind of arbitrary, right? Whether we call it block 1 or block 2. But make sure you understand why these different effects are grouped together. Okay, and then this just goes into the even-odd rule. I like to think of these together. Okay, I'm going to skip over some of this. Okay, so now we're going to do this in general, because everything we've done up to this point,
yeah, the exact same thing,
is 2 groups of size 2 to the k minus 1. Okay, so what if we need this in general, where q is not just 1, but q is anything? So we want 2 to the q blocks of size 2 to the k minus q. So for example, we could use the even-odd method with 2 defining contrasts to get 4 blocks. Well, we've already done that. Okay, sorry, we did the opposite. So that would be new. So 2 defining contrast to get 4 blocks. Yeah, that we have not done at this point, sorry. Then for each of our factor level combinations, we do the same thing where we just divide, is it even or odd, and split it as 4 groups this time, where one group is even/even, another group is even/odd, and then the other is odd/even, and then odd/odd. So let's see this. So here we have a 2 to the 4 design based upon our 2 defining contrast, ACD and ABD. Now, I remember being so confused when I first learned this. How do you know your defining contrasts? And right now, I really want you not to worry about where these defining contrasts come from, because they really have to be informed by the context. So remember, the defining contrasts are just those contrasts we're willing to throw under the bus. So I can't say, oh, ACD and ABD are always going to work for 2 to the 4. No, it depends on what you're assessing in your 2 to the 4 experiment. Okay, so don't pay inordinate attention to why I picked ACD and ABD as my defining contrast. Just look at the procedure, okay? Make sure you understand this procedure. I apologize, I had to stop for a second. There's a little background noise in here, but I'll try to minimize that as much as possible. Okay, so let's start with the grand mean. I'm not going to run through all of this. It's your responsibility to make sure you've got all of this. For both of our defining contrasts, the grand mean is defined as even. Why? Well, if we use the even-odd rule, we get 0 matches for both of those defining contrasts, and 0 is deemed an even number. Okay, we'll call it that for now. Versus if we look at, let's pick something more interesting than A. Let's pick B, okay? So B shows up in only one of those defining contrasts. So the first one is even because it has 0 matches, and the second one is odd because B matches. So notice how it gets coded as even for the first defining contrast, but odd for the second. Let's do an odd even, BD. So there's an odd number, specifically the D shows up in the first contrast. In the second defining contrast, both B and D show up. So it's defined as even. And then let's pick on an even. Or sorry, an odd. Let's just do D. D shows up one time in both of those contrasts, as does A. What's one? A, B, C, D, all 4 show up 3 times in both contrasts, so that's also odd. Let's stop here, but do make sure before you move on to the next video of notes, make sure that you understand this coding and how these defining contrasts define our 2 groups. Then we'll take it to the next level in the next set of, or the next video.